Or where do we go here? You got that pulled up stuff.
See, so that's why we have camera. So Professor Sebastianovich, you are off.
You are half and half. No. You gotta go back that way, dude.
No, I want to see how far I have to go to be completely off.
Okay, so everybody knows you have 20 to 22 minutes for presentation, but not gonna be. Don't worry, if it's 22 minutes and 10 seconds. But if you go to, like, we are going over too long, I'll let you know. Just stop. The other thing to let you know is the two, Formula Hybrid. There are two projects, two design projects that we decided sort of during the semester, but they're taking two time slots, but they're not strictly divided up into two. The two presentations are gonna be more or less.
We're planning on combining the two.
It's split, so like,
We gave them freedom to use time as they wanted, but they are gonna take two time slots and present two different designs. One for the brakes and one for the price.
Well, the evaluations are then. Yes, it's like.
Together is fun.
Okay.
Yeah. Okay, whenever you are set, it
are we
is,
for PBS or no?
no, he is gonna be,
Okay.
watching online, I believe. So whenever you're ready, you can get started. We're right on time.
Good afternoon. So we'll be presenting the Formula Hybrid front upright and braking system design. I'm Rila.
I'm Bradley Rosencrantz.
I'm Reese Christopher.
I'm Chase Monahan.
I'm Gideon Bid. And Cruz on the cover. So a little bit of background information and motivations for this project. So geometric constraints on suspension, some key drawbacks from last year's 2025 suspension design team. The existing uprights were forced to be installed inverted because of incompatibility with our current front mounted steering rack. This causes additional restrictions on key suspension parameters such as kink-wing inclination, scrub radius, camber gain, and tie rod adjustment, reducing the number of feasible suspension kinematic designs. Struggles in the brake test. So historically, we've struggled greatly with our with succeeding in our competition brake test to get on track. This test requires that we lock all four wheels simultaneously in a designated braking zone. These shortcomings indicate that the current braking system and this integration does not meet our requirements. Additionally, as the upright's being redesigned, it gives us an optimal time to reassess multiple caliper mounting types. Out-of-date vehicle parameters. So the current vehicle uprights were designed back in 2016. For a vehicle that weighed approximately 1,300 pounds, whereas now it weighs about 800 pounds, making it significantly lighter and thus a lot more room for us to refine the design and reduce mass, increasing our performance and interesting manufacturability as well. Age and maintenance concerns. As I said earlier, in 2016, these uprights were manufactured, putting them in about a decade old now. And at that age, there's limited, especially with COVID and a lot of administrative changes within Formula Hybrid over those years. There's limited knowledge on their fatigue history, maintenance, and storage. Prolonged use and environmental exposure and potential material degradation is also a concern, making using them for even longer a point of concern and safety.
So then some of the parts, well, this is a complete list of all the parts that we are actually going to be modifying. A key thing to note here is these are only the parts that are going to be on the front axle. We are not touching anything on the rear axle in this project. So if it's listed here, we are going to change it in some way, shape, or form. If it's not listed here, we are not going to touch it. If something we change here changes something for the future in a different part on the car, it will be up to the Formula Hybrid team to adjust accordingly. And then a few overall major goals that we had for this project. The first one was to reduce the weight of the fully assembled just our parts on one half of the car by 25%. So this would take us from about 17 pounds currently down to 12.5 per side. So it would get us down to about 9 pounds of loss there. We also want to make sure when doing that, we are still maintaining a factor of safety of 2.76 against yielding. We also want to make sure that we design reliable brakes. This is really meaning that we can pass the brake test, which means we can simultaneously lock both the front and rear brakes. Because we aren't touching the rear brakes, this is mainly based on adjusting the fronts accordingly. The final major goal we had was to have all of our parts manufactured and ready to go on the car by March 14th. This would allow us to do some testing and fix any minor little problems that we had before the actual competition in May.
So the constraints that we're limited to is the current geometry of the suspension. The picker points of all the control arms, those cannot move. The packaging must be done around the current OZ racing wheels, as those will be getting reused. SAE has their own rules that we must comply to in order to pass inspection or test at competition. All systems and components will be assembled or installed by March 14th, such that there's adequate time for testing and validation that we need to perform. And then all four wheels must be able to lock into braking. This can happen either with the fronts locking first and then the rears, or ideally, the front and rear would lock simultaneously. So the project division that we came up with, just initial discussion in our project, it makes sense for us to split it up with the upright and bearings, and then also the braking and spindle. The decisions will be made per part, not rather than a system as a whole. So there'd be lots of minor decisions that we can make along the way. Moving into the upright knuckle design objectives, the upright needs to be designed such that it's compatible with the control arm pickup points, and those aren't changing. The tie rod pickup point needs to be adjusted such that it's in line with the steering rack. The brake caliper mounting points are getting moved to the opposite side of the tie rod pickup point for packaging reasons and to reduce additional stresses on the upright. And then we need to minimize weight. The current upright is around 1.7 pounds, and we need to cut weight where possible such that the whole assembly is reduced by 25%. And then finally, we need to maintain reliability. We use the Pugsley method to determine a factor of safety of 2.76 against yielding. So we'll need to make sure that that's maintained.
So in order to design our upright assembly, we need to figure out what kind of loads are going to be going into it. So we looked at three main load cases, the first being steady state cornering. So this is taking corner at a constant speed. The next being pure braking, so driving in a straight line and slamming on brakes. And then finally, we have our 3-2-1 combined load case scenario. So in our research, we saw a lot of other Formula hybrid teams have used this load case scenario as a kind of worst case scenario to design their suspension around. So what it is 3 G's of vertical acceleration. So you can think of this as hitting a bump, 2 G's of lateral acceleration or cornering, and 1 G of braking, all simultaneously. So starting off, we use Newton's second law to calculate the vertical tire force on all 4 tires at the same time. And this is 2,400 pounds combined. We then transferred this load from the inside tires to the outside tires using the lateral load transfer. So this is dependent on the vertical load, the lateral acceleration AY, the center of gravity height above ground H, and then the tire track width T, the distance between the left and right middles of the tires. And then in a braking scenario, we transfer the weight from the rear tires to the front using total lateral load transfer distribution. This was calculated in terms of a percentage and is dependent on the longitudinal acceleration, center of gravity height again, and then the wheelbase length, the distance between the centers of the rear and front tires. So here are loads calculated after transferring. As expected, the front left tire experiences the highest load because if you think of it, you're taking a right-hand turn, the load is transferred to the outside tires, and then as you slam on the brakes, the load is transferred to the front tires. We then related this vertical load to the lateral load Fy through slip angle. So slip angle is the angle between the direction that the tire is facing and the direction it's actually moving. And then we related the longitudinal force to the vertical force through slip ratio. This is a ratio dependent on the wheel's angular velocity compared to the car's actual forward velocity. However, this relationship isn't linear, so we had to create an empirical model where we imported tire data for our Hoosier R20V tires, fit a curve to this data using the magic formula, and then swept through various slip angles and ratios to find where the maximum possible lateral and longitudinal forces occur at. So here's our final forces. As you can see, our 3-2-1 combined load case is the highest force, with the longitudinal and lateral forces being scaled by that 3G vertical acceleration.
Then moving into the design concepts that we came up with, we had three options. The first one being the density-based topology optimization. This one focuses on simplicity while still removing weight, allowing it to be machinable. The tie rod pickup point is relocated to be in line with the steering rack in the Z direction, as this reduces the load path length between the steering rack and the upright, enabling a more direct transfer of steering forces, lowering bending moments within the knuckle, and ultimately reducing material requirements and the overall mass. The brake caliper mounting location is also flipped to the opposite side of the tie rod pickup point. That's more efficient for packaging and reduces extra stress on the upright. This concept was designed around the use of 7075 T6, and it's to have a chromate conversion coating to enhance corrosion resistance, and then to further improve stiffness and steering response, a bonded carbon fiber skin is applied to the exterior, increasing torsional rigidity and improving steering feedback without a significant mass penalty.
The next design concept is a modular design concept. So this design focuses on having our upright be able to have different brake mounting positions as well as tire rod mounting positions. The advantage of this is that we can use the upright for future vehicles for different suspension geometries, brake mounting positions, and tie rod positions. This also will cut down on the lead times for redesigning and remanufacturing any of these components. The parts of the upright, as instead of redoing the entire upright, we can just focus on solely redoing the brake mounting or the tie rod position.
And then our final concept is a level set topology optimized concept. Level set method is a method in ANSYS where you give it a structure with loads and constraints, and it'll kind of eat away at the material depending on what criteria you set. So for this concept, I told it to maximize the stiffness while reducing the weight. And the main pros of this design are reliability. It's one full part, and you'll have a very high strength weight ratio part. However, it's a very natural forming design, so it's very difficult to manufacture. Then here's our final decision matrix comparing each of the three options. As you can see, initially, the modular design wins because of its high design flexibility. However, we will be pursuing a level set concept because we have the rare case scenario where we've got a sponsorship from Evolution Manufacturing. So they have offered to let us use their DMLS or 3D metal printing services that will be able to produce this complex level set geometry. And their main constraints are that it would be up to $10,000 in sponsorship, which they said equates to about less than 30 cubic inches per upright, which should not be a problem. We're expecting, if we're meeting our weight goals, it should be around 20 cubic inches. And they also said it's a 1.5 week lead time. So if we're trying to meet our St. Patty's Day deadline, we would have to have our design finalized by late February, early March.
So how we chose material, our initial research led to 4 possible materials. We looked at aluminum 2024 T3, 6061 T6, 7075 T6, and then grade 5 titanium. We looked at important material properties like ultimate tensile strength, yield strength, fatigue strength, elastic modulus, density, and its specific strength. From Evology, we had advice to use aluminum 10Mg for the DMLS, so we included that material as well. And we looked at 5 criteria for selection. We had cost, machinability, mechanical properties, specific strength, and availability. Going through the decision matrix, it ended up being that 775 T6 is the best option, but due to the sponsorship from Evology, we will be using aluminum 10Mg.
Then moving on to the bearings. So initial research considered 2 types of bearings, ball bearings and tapered roller bearings. However, we concluded that we will be using tapered roller bearings as they're able to support both combined axial and radial loads. as well as they have line contacts and point contacts that roller bearings would have. This provides higher stiffness and higher load capacities for tapered roller bearings. Additionally, tapered roller bearings we found are more resistant to moments that will be seen in the bearings, and we can also have preload capabilities with tapered roller bearings. Going into the bearing selection, we use the SKF bearing catalog to determine what bearings we would like to use and do the necessary calculations for them as well. The SKF catalog is a collection of manufacturer validated bearing data, which complies with ISO 281 and ISO 76, which are the dynamic load ratings and the static load ratings for bearings. The catalog supplies the dynamic rating and the static rating, as well as bearing specific constants, which account for the internal geometries, the contact angles, and the load sharings between rollers in the bearings. Going into the design objectives, the design objectives for the bearings are that they are capable of supporting both radial and axial loads, as well as the moments that we see. The target life should be met. For example, we chose 1,000 hours, which is a gross overestimate. And additionally, the bearing should be compatible with the spin node diameter and fit into the upright. For the load inputs, as Chase previously mentioned, we'll be evaluating the different load cases of steady state cornering, pure braking, and the 3-2-1 defined loading, which are then the loads from those cases will be used as inputs into the bearing calculations alongside vehicle speed, which we will be using the maximum vehicle speed of 62.5 miles per hour as specified in the Formula Hybrid rulebook. Then going into the rotational speed calculation, just converting the vehicle speed into RPMs for the bearings, and that will be used to later calculate the load or the life of the bearings themselves. For equivalent dynamic load, SKF specifies 3 different piecewise functions for single row or for tapered roller bearings. This being the single row tapered roller bearing piecewise function, where Y is a bearing specific constant that will be found in the SKF catalog when selecting candidate bearings, and FR and FA are the radial and axial loads. Next is matched piecewise function. Similarly, it has the same layout, but it uses different bearing specified constants of Y1 and Y2 in the catalog. And then double row bearing has the same piecewise function and uses the same constants. As for the selected bearing arrangement, we went with the paired matched single row bearing since it's able to support both axial and radial load, as well as it has excellent handling of the moments that they see. Additionally, the geometry of the the single row bearings is much more flexible than the other two, and it is preload adjustable. And for the arrangement, we chose to go for the back-to-back arrangement since it came with those moments. For the governing equivalent dynamic load, that would just be the 3-2-1 load case scenario, but it would be selected from the 3 different load cases. And for calculating the bearings revolution life in millions of revolutions, that is the calculation that utilizes the target life hours that we specified, as well as the RPM, and then converting it to. For required dynamic load rating, the required dynamic load rating is calculated as seen on the screen, where P is the governing dynamic load, which was selected for the 3-2-1 load case, and the lowercase p is a specified value for tapered roller bearings in the SKF catalog. Then for the required static load rating, the kind of static load rating calculation can be seen on the screen with the equivalent static load calculation, which is then fed into the static load rating calculation with a variable XO, which is configuration dependent. 0.5 is the value for single row tapered, and 1 is the value for paired or double row. And the safety factor is the safety factor we selected of 2.76 using this previously mentioned method. So to actually complete all these calculations, we wrote MATLAB scripts. So the MATLAB scripts will take the inputs of the load cases and calculate required and required static and dynamic load ratings. These static and dynamic load ratings are then used as a minimum requirement for when selecting candidate bearings. The candidate bearings we choose from the catalog should either meet or exceed these load ratings. And then inputs of the radial and axial forces, vehicle speed, the target life hours, and other very specific constants are then used to calculate these. The outputs of these MATLAB scripts will then be the equivalent dynamic load, the equivalent static load, the required dynamic load rating, the required dynamics, or the required static load rating, and the calculated bearing life for all of the candidate bearings that are fed into the scripts, as well as the static safety margin for each of those candidates. Here's an example where you can find this information in the SKF catalog. So on the left, you can see the static and dynamic load ratings, which are per bearing. And on the right, you can see the actual calculation factors per bearing. So as an example, we calculated for the current spindle diameter, which is about 1.5 inches. So we selected candidate bearings out of the catalog that were 1.5 inch inner diameter or greater. And then we fed all the information for the bearing specific factors and the required or the life hours into the scripts, and then it outputs the following results. So based on these results, we'd be choosing the bearing on the left since it exceeds our 1,000 hours requirement.
We're going into like the spindle and braking assembly, kind of four topics that we're going to touch on. There will be the braking dynamics, current brake system configurations, rotor design concepts, the overall final design concept, and spindle design choices and calculations. Going into brake dynamics, more things that we're mainly looking into, which is the total braking energy, the load transfer, the traction limit, and the braking force. Now for the current braking system, the thermal capability of the brake system is that we do not overheat that much. As I looked into one of the heat transfer of the current brakes, they are stainless steel and have a mass of 1.6 kilograms. For a typical braking curve, well, going from stopping from 25 miles per hour to 0 miles per hour, converting kinetic energy into thermal energy. It was found that the front rotors have temperature change of 12.3 degrees Celsius per second with the 1.2 Gs of deceleration, and rear rotors have 3.32 degrees Celsius of temperature change in the rear rotors. And there's some yeah, so we looked at braking forces at the contact patch. You had two objectives here: calculate the actual braking force, and calculate the theoretical maximum braking force. The actual braking force first calculates clamp force developed by your pistons using the number of pistons you have, your line pressure, and your caliper piston diameter. Your torque is then calculated by using that clamp force, your pad quick friction coefficient, the number of pads, the rotor diameter, and your caliper piston diameter as well. And then you can get your braking force by dividing that torque by your static rolling radius. Theoretical maximum braking force was found by finding the load transfer from your rear axle to your front axle based on your front axle weight, your CG height, your wheelbase, your total weight, and the acceleration you're experiencing in G's. And then multiplying that dynamic load on that tire by your tire's friction coefficient. Using those two forces, you can develop the surface adhesion utilization plot. A little bit about how to read this plot real quick. The blue lines indicate front axle, the red lines indicate rear axle, the white lines indicate actual braking force, and the dark lines indicate theoretical maximum tire force. The intersection of theoretical and actual braking force indicates axle lock for that respective axle. As you can see here, this dark blue line intersects with this light blue line at approximately 1.3 Gs. And then desirable outcomes out of this system. Ideally, you'll have simultaneous lock where both axles lock at the exact same G. Second, front axle locks before the rear, and lastly, the rear axle locks before the front axle. Over here is our current system. The current system, as you can see, the rear axle locks before the front axle, with the difference of 0.2 G is between when those two axles lock, making this not ideal as when you lock your rear axle before your front axle, you greatly increase your chance of losing control of the vehicle, which is the automatic fail in our test competition. Design concepts. We looked at fixed rotors and floating rotors of various retainment methods. Although floating rotors offer greater weight savings and thermal expansion properties, they couldn't compete with the superior manufacturability, the reliability, and cost of the fixed rotors, especially with how the team operates. After every track event, we inspect every single critical component, including the brakes, thoroughly. So any cracks or damage that would happen to our rotors would be caught very quickly, making replacing those damaged parts quick and easy, especially with this type of geometry. The cost of manufacturing and parts is low, and turnaround is quick.
So there are 4 different categories that we're looking to for the design concepts of the brake rotors. Where thermal overheating is not an issue, as mentioned earlier. For weather, we do not face any like strong weather conditions. The worst weather conditions that we face is heavy rain. And for mass, since we don't overheating is not an issue, we could maximize the amount of mass that we can take out of the rotor. And for stresses, we want to create kind of geometry for the rotors that the thermal stresses are not concentrated in some general areas. And for caliper location, we were looking to the optimal location where we could place the caliper, and it depends on the pickup, the tie rod pickup point. And usually it is placed on the opposite side of where the caliper is placed. For example, on our case, the pickup point of the tie rod is in front of the front axle. So we would be putting it via behind the front axle. So it minimizes any additional stresses that could happen on the upright.
System configuration. So we narrowed our search down to 3 system configurations. The first option being a 4 piston fixed 1 1/4 piston diameter rotor, the Hayes Alpha, or caliper, sorry, the Hayes Alpha, and pairing that with a 0.61 mu pad and a rotor diameter of 9.75. The second option being a 4 piston fixed caliper with a piston diameter of 1 3/8, a pad mu of 0.5 and a rotor diameter of the same 9 3/4. The last option being the same 4 piston fixed 1 3/8 caliper paired with a 0.6 mu and a 9-inch rotor. All of these use long curving slots and fixed rotor mounting styles based on what we determined earlier. Here is the result on the surface adhesion utilization plots for each of those respective systems. As you can see, option 1 and 2 produce very similar results, with system 2 being slightly better as they can achieve a very slightly better maximum G-force. But the difference between when the rear is locking and the front's locking is about the same between 2. System 3 clearly creates the best system where both axles lock almost simultaneously, which is exactly what we want in our best case scenario. System, we looked at the packaging and for each of our options. Here in option 1, you can see that the alpha caliper does not fit in our maximum allowable diameter inside of our wheel well, as it eclipses that line over there on the top. The other 2 options both fit within our geometric constraints, as seen here. Final design concept, we weighed manufacturability, reliability, weight, cost, and design flexibility as we did earlier with the upright. But additionally, we looked at stopping distance completability, stopping distance being a result based on the surface heat and utilization plots. And bleedability being a geometric thing, as you can see here with the alpha caliper over there, this only has one bleeder port right here. Meaning this is a directional caliper, it can only be mounted in one orientation for air to be expelled from the system properly. However, here with the F435 caliper, you can see it has two bleeder ports, therefore, no matter how this caliper is oriented, as long as it's not horizontal, there will be a bleeder port facing to the top of the caliper or at the highest part of the caliper, meaning air can be expelled from the system. Here is a mock-up of how our final design would look inside of our wheel. That's transparency, which is transparency is unchanged, so you can see our components. Yeah.
So now let's talk about the spindle. So the main constraint we have on the spindle is that it must be able to attach with the current wheel, which has a 4 by 100 meter square bolt pattern. Otherwise, everything else that the spindle is touching is being changed by us pretty much. So those parameters, while still will affect the spindle, aren't set in stone, so they aren't full constraints yet. For each of these design options, we will be considering 5 different criteria, which include the manufacturability, the reliability, weight, cost, and design flexibility. Real quick, this is pretty much the exact same material selection as Reese talked about with the upright, except it doesn't have the aluminum 10mg, which was the Evology like specific material. Pretty much same conclusion. If we can, aluminum 7075 will be our best option. But if you compare the 3 aluminums, they all have relatively the same score. So if we can get one for super cheap, it will probably be the option that we go with. The first spindle design that we came up with was a modular design, which is broken into 4 different parts. It has the inner tube here, and then it goes to the hub that connects to the actual wheel. It has a disc here that connects to the rotor, and then the one part that isn't pictured is the little key that allows all of them to be connected and rotate together. So the best part about this is the availability to change designs on other things. If you had a new wheel that was coming in that needed a completely different bolt pattern, all you would have to do is change this one part to reflect that, and then you wouldn't have to redo the entire spindle anytime you had a minor little change. The worst part about this design is the tolerancing issue. Because of this key, you want everything to be super tight together. And if it's not, you're going to introduce a bunch of unnecessary stresses and impact forces that will cause this key to be in a horrible condition where it can easily break. Other than that, just overall, this got a score from the decision matrix of a 32. Our second design was a complete one piece. So instead of having all those different pieces, it's just manufactured out of a solid piece of metal. Best part about this one is it reduces the, it is better for reliability and for weight. Weight meaning you don't have all the extra spacers and fasteners and all that. It's just one piece. You're not worrying about connecting anything. And that the reliability is you don't have all those extra connection parts. You don't have extra joints or anything that can add extra failure points in your system. This one overall got a score of a 32.4, so a little bit better than the last one. And finally, we have our hybrid design, which has the kind of complex geometry from the last design, and then it just is connected with the simple disc here, that this disc is just detachable and this connects to the wheel. Best part about this one is the reliability is still super up because you're still you mainly have the forces in that, but then you also have that design flexibility where if you did need to change wheels, you would just need to change this part instead of changing the entire thing. Worst part about this one is all the extra added weight. So as you can see, this extra disc here is not in any of the other parts. So you're adding weight there. Not only that, you would have to add bolts that connect these two parts together, which with the 4 bolts, you're gonna add up quick when we are trying to reduce the weight. Overall, this got a score of 30.5. So the final spindle choice that we went with was the second option, which got the highest score of 32.4. This had super high ratings in the reliability and the weight, but it had lower ratings in the design flexibility, cost, and manufacturability. For manufacturability, we would probably make this out of a lathe and mill like combination. And because we have those tools at MSOE, it wouldn't necessarily reduce the difficulty of doing it, but it would reduce the cost of if we had to outsource this to somebody else. The cost as well, we have been in contact with someone from Scott Forge that is willing to sell us billets of material for super cheap, which will limit the actual cost overall. Unfortunately, there's not much to do with the design flexibility on this, but the design flexibility was a criteria that it was more of a, hey, if it happens, it'd be awesome, but it's not like a, if it doesn't happen, this is like an end all, we can't do this.
All right, so moving into the next steps for the upright, we'll need to finalize the tie rod pickup point and zigzag coordinate system. This will be done through optimum kinematics. You see that picture on the top right there? We build a stick model with all the coordinate locations, all of the different control arms on the upright and then on the chassis as well. And then we, when we set up the system model with the inputs, we'll be able to create a region where we generally want the tie rod pickup point. And then what the software will do is tell us exactly where it should be based on what we put into the system. We need to get the specific location for the tie rod because we need to increase the steering angle without binding. We need to increase the linearity in the steering system, which is done by getting the pickup point as close to in line with the steering rack as possible. And then ultimately it will decrease the weight of the tie rod by shortening the distance that it has to travel. Another result from the optimum kinematics will be the loads transferred directly to the upright. And then we'll need to use ANSYS to create a level set topology solution. That will also give us the brake mounting points. And then we need to validate the solution. So we discussed the plug-in method for the safety factor 2.76. We'll have to check the max equivalent stress in the upright to ensure that that holds true everywhere. And then Evology also gave us constraints for manufacturing, so we'll have to ensure we follow those. And then we'll also need to determine the optimum printing direction as well.
For what's next with the bearings, so next up, we will need to be able to incorporate shared loading across pair bearings into the MATLAB code. The image on the right just shows the different load cases that SKF specifies for shared loading in match bearing arrangements. Additionally, we'll have to calculate the actual bearing requirements based on the completed load cases. And finally, we'll have to select an appropriate bearing based on the spindle diameter with that is calculated.
For the brakes, we'll be performing brake MBA on the brake orders and try to optimize the slot spacing. And also, we're gonna partner with Hayes and their dyno to validate our design.
And finally, what's next for the spindle? Not a bunch going on here, really just doing some FEA analysis to make sure that our sizing is correct and we aren't gonna have any spaces where we're not meeting the 2.75 or 2.76 safety factor. Do some hand calculations to verify that, as long as calculate the optimal diameter we can have. Other than that, it's really just ordering the material and actually getting the part cut. Any questions for us?
You want to go ahead? Okay. Very nice. You covered a lot of ground there. Yeah, I think I have a few questions for almost everybody.
Yeah, you did a nice job of summarizing everything you did, because I know it's like a lot of decisions. So let me see what I made a note of. Of course, I'm going to ask you about the material choice, the aluminum, silicon, tin, magnesium. Does that need heat treating?
I don't believe so. I don't think they mentioned. No, they did not.
So it's as printed
Yes.
and then
Done
done.
by a machine for surface finishes, like the critical zones, like where the bearing would be and everything,
Okay.
contact points.
So then you'll have to collaborate or coordinate with them, like you'll have a design, and then to know what machining allowances are required from their process, you'll have to modify your design.
Yeah.
So when, with your week and a half turnaround, like make sure you have some time in advance to confer with them. When you have a design, it's really still preliminary, and then they're going to give you feedback and they're going to say, change a few things or add some tolerance for allowances.
I believe what they told us during our meeting was that they add 10,000 of material onto all of our critical interface components.
And you'll have to identify, and that might change with printing orientation and things like that. On the bearing selection, I'm just curious about these things. I'm not trying to like trip you up on anything. So you said there have to be rated for radial, axial, and moment loading on the bearings. Do you have an idea with our particular problem, which one of those three is like the most severe? Like, is it really limited by axial, or is it really limited by the moment, or?
Off the top of my head, I do not know. Assume that it is mostly limited to likely for axial. I do not think the moments that are seen.
The moment, see, I'm never sure because the wheel is offset somewhat from the bearings, but maybe not as much as I think. Okay, yeah, it's good to like, even though you're crunching through the details and all the numbers, and there's a lot there, just to like back up and say, okay, ballpark, what is the most severe thing that could happen to these? Is it the, and then go back to your design, and is there anything we can do to reduce that? I have more bearing questions. In your final two choices that you showed for bearings, there was a significant difference in weight. One of them was like 2.5 times heavier than the other.
Yeah. So
That seemed odd to me.
that's just
Yeah.
options for foot selected for internal diameter of 1.57 inches.
Yeah. Any idea why the weight, like if those were the two final choices, why they're so drastically different in weight? Since you're trying to reduce weight, that's your number one goal.
Yeah.
And I think you went with the much heavier one. If I recall, the one that you picked for your final was like more than double the weight of the one that you didn't pick.
Yeah, and that was solely based off of the life rating or the life hours that,
But did they both meet the life rating?
no, so the lighter one actually was at around 500 life hours and.
Oh, okay.
The heavier one was at about 2,000, so.
Okay. So I guess you could decide if that lifetime needs to be revisited.
Yeah, so we discussed
we were
that.
discussing
If there's a lot of weight
earlier,
there
just
to be,
that 1,000 hour life is basically, we did some gross estimates on all the testing we can possibly do with these over basically a 5-year lifespan of these components.
no, yeah, I believe you. So I'm not saying you have to decide on the
Fine.
now, but maybe it's a good to look at that and see if it is what you need, that's what you need, and you have to go. But if you just were kind of like winging it on the lifetime you need, and you have a bearing option that's a couple of pounds lighter. On the heat generated in the rotors, you had some estimates up there, which is good. Did you assume that the amount of energy from braking is just going into the total mass of the rotor? So that's like an average temperature?
Yeah. That was like,
Okay, so do you think that's what really happens? Yeah, so the heat's generated and then it transfers away as you're returning. So that's kind of what we talked about maybe as a topic for you to look into in detail. Are you interested in that? Okay. So yeah, so that's like a good preliminary, but you know, it's a ballpark estimate and you know what for sure. So what do you know for sure about your estimate? Is it conservative or non-conservative? Well, as a design, it's non-conservative because you know for certain that locally the temperatures are higher, right? So it's an approximation, but you know the reality is parts of your rotor are definitely getting hotter. So in that sense, it's I would call it non-conservative as a calculation. Did you consider the pads and rotor selection? You have a lot of haze options. Did you consider other options beyond haze?
We did briefly, a lot of the options we looked at, were from Lula, and they didn't really have a lot of options with the ranges we needed. They were all either low or too high.
Option low or high?
They were all around the 1.25 inch, bore diameter like alpha, or they were much larger at like 1.5 inch piston, bore diameter, which is larger than that second option we had, which was 1.3
Okay.
inch.
Are there other competitors? I know I'm saying look at your competitors, but
Wait on.
like as a,
Got those calipers for
We
free.
did also get.
Which came in.
I understand that, and that's an incentive for the team to choose them, but for your senior design project, you have to approach it as completely open-minded to any source.
Yeah, I plugged in some of those Willwood
Like I'm-
contenders into our initial search for all of our, like, to get it narrowed down to those three options. We did look into some of those external options and they're really lined up to
Yeah.
exactly what we needed.
Like I completely understand that. And like what you said about the choice of the upright design, like we did our design rubric and it showed this, but we have this one-time opportunity to get $10,000 worth of printing from Evalogy. We're going to take advantage of it. But I still want to see that you went through the decision matrix and were really open-minded about how you approached it. Just a general comment about using the term optimize or optimized in front of engineering professors. I heard that a lot today, and that has a very specific, like, don't overuse that. If you're just picking a good design, you are not optimizing it. And even with the upright design and the, I'll just toss this out here. If you really wanted to get in depth, you would look at the optimum kinematics and the stress analysis combined at the same time into some sort of like meta analysis, because the things that you're changing in that you're getting from optimum kinematics and where the pickup points are going to be, that influences the loading that goes into your stress analysis. And if you do them one first and the other one second, you're missing probably what the actual optimum design might be. You know what I mean? Yeah. That's everything I have. That was enough. You want to ask some questions?
Just a couple. Do we have anything from Dr. Sebastian?
No, I don't know.
You just didn't want to show up to that? He emailed us that he was gonna watch it later. I don't know if he's.
Oh, watch it later. Oh,
Because I didn't see him come online. So he will email questions at a later time. I'm just saying that.
Presentation is not open, so
Right.
where did that number come from?
That was calculated using the Pugsley method, so basically a bunch of different criteria like, how much of a danger this is to a people.
Okay.
And it gives you a table of factors and then you multiply all those factors together to get your sector big.
For the one part that's made out of DMLS, it's very sensitive to the orientation of the, what is the sponsor gonna help you with?
Yes, they're willing to talk with us and with some backward conversation on optimizing that orientation in their machine to get us the best result.
So orientation, process parameters, post-processing are big variables in
Yeah.
that. So you may be in for a surprise at some point in time. It does sound like magic that you have the part made, a very strange topology made from an additive method, but there is a lot more to it than just printing out. Also, the spindle seemed like a very complex one piece. Or do you really want to pursue a one piece spindle?
We thought that with it being more reliable than the other two, and the manufacturing will be really tricky to figure out, but I think eventually we will be able to hopefully get it. And if we need to take, so you know how it was kind of like a star shape, if we need to take that and make it just circles, I don't think that will necessarily hurt the overall design that much. It will add a little bit more weight, but it should make the manufacturing process a little bit easier.
Part of it is cost consideration too, because to make that, you're gonna start out with a huge chunk of aluminum and you're gonna throw like 80% of it away,
Yeah.
but you still gotta buy the original billet.
Do you know what the price was that he was offering us at Scott?
Or like 50 cents a pound.
Yeah, but like,
Yeah, it's
As a
gonna
design.
be a very,
Yeah, it's gonna be very affordable.
yes, it's gonna be a very thick bill.
besides whatever like donations or
Yeah.
sponsorships you get, that's a very big expense
Yeah,
when you take a huge billet of material and throw most of it away.
yeah,
In any real manufacturing setting, that would not be possible.
Yeah,
Yeah,
You'd have to think of other ways to manufacture.
like people make things like that where they forge the component initially just to save all of that
save all of the material.
material and machining cost.
And it's gonna take you maybe a couple of weeks to make it.
Yeah,
right.
That was all right.
Okay. Thank you. Right, we can do the switch.
They were up there for 50 minutes. Oh, my knee actually hurt.
Don't lock your shoes. I know, I was all over the knees. I need.
Your other roommates just not showing up or something? Just taking the F?
I mean, they're all in like sub teams.
Are you guys gonna be two separate presentations?
Yeah, that's what some
Okay.
guys. Yes.
Yeah, they're not the hallways.
Well, we can go.
This move. They're working on the same like car. Yeah, these are two different things.
I think that was good. You used double the time, but I don't think you're gonna double the question.
It seemed like a lot, but not really, considering it was two, so you all set to go?
Okay.
All right, whenever you are ready.
Hey, so I'm Max.
And I'm Jacob Torongo. Our project was on the SA Baja vehicle suspension redesign for the component. So a little background on the actual Baja team itself. They are club here at M3 and they go out to different locations and they go through different competitive tests such as rock climbs, jumps, maneuverability. And they hired us to redesign front suspension. Part of that was the gearbox and steering, which Cody and Nathan will get to when they show up. So we wanted to improve the geometry, maintain / improve the weight, and then improve the packaging of the suspension itself. The knuckle on the car was already designed in past years, and we felt that it maintained our goals, so we did not alter the knuckle, and our design mainly focused on the upper and lower control arms. Some of the requirement or design objectives was we wanted a minimum of 8 inches of wheel travel, which was currently on the car. A durability for a factor of safety of 2 during normal riding conditions. We wanted to reduce the unsprung mass by around 15%. And we wanted to have our geometry to have a toe of 0 to ¼ inch toe in, and then have a -1 to -3 caster with a camber of positive 8 to 10 degrees. For some of the constraints, we wanted to make sure that it was packaged appropriately and that we did not have to change the chassis mounts of the car so much. With our design, the lower chassis mounts are going to stay as is, and we are just going to be altering the top chassis mounts as we are redesigning the stock mount location. We wanted to stay underneath a budget of $1,000 and comply with all the SAE 2025 rules because we didn't want them to show up at the competition and just be disqualified before any tests began. For the current design vehicle, it has a total weight of 4.91 pounds, just including the upper and lower control arm, not the knuckle or anything else. The shock, as you can see, was mounted to the upper control arm. And the geometry for it has a track width of 60 inches, which is the outside wheel to the next outside wheel. It has a camber of -10 at full compression, and it has a static caster of 6.2 degrees, which we wanted to increase. And it has a suspension travel of 8 inches. The first design that we researched was an A-arm design. As you can see, you have the knuckle here with 2 ball joints, and then you'll have your upper and lower control arm. All the designs that I'm going to go through has a double wishbone / A-arm design for the lower, and we're looking at different upper control arms. For the A-arm design, it provides a strong structural triangulation, and it maintains good caster and camber throughout wheel travel and whatever tests, such as like the rock climbing. It's proven to be reliable and durable, and it is definitely the stronger out of the designs that I will go through. It's also easy to tune and improve for performance. The next design is a J-arm. As you can see, it reaches around the shot. It's definitely easier for packaging, and it's less weight as you do not have another arm reaching around the shot. Because of that, you'll have a higher stress on that arm, which creates a moment there. It allows for greater flexibility for shock placement for different geometry. Like I said, it introduces a higher stress as well, but it may require stronger materials and gusseting because it does not have that second arm reaching around the shock. For the last design was the single bar, which is in my opinion, the worst out of all of them because it is not very structurally integrable. And the benefit of it, it's very low cost and it's very simple to make, but it's very suited for like things like golf carts and lawnmowers, not for some off-road vehicle that is going to be going through extreme conditions. Another thing is that it sacrifices caster and camber throughout the competition, and it doesn't maintain those good geometry values. We made a decision matrix or a design matrix based on the 3, with obviously the A-arm winning. Our highest category was geometry, as the Baja team specifically said to us that that was the most important category for them, that they wanted to maintain the proper caster and camber throughout the competition. The next highest being the durability, because we wanted the suspension system to be safe and that they don't just break during the middle of the competition. Then next we have packaging and weight being 15%. And then we have cost and ease of manufacturing being around 10%. The only category that the J-arm won was the packaging, as it allows more space for a shock mount location. But overall, the A-arm beat the J-arm and single bar in most categories, losing just the single bar for packaging being 5 because there's pretty much nothing there.
So going into our final design, so for our final design, the total weight came out to 4.63 pounds, which was a 6% reduction from the previous design. This design used the same poly tubing that the rest of the chassis uses currently. Obviously, still material selection has to be done in future work. For packaging, as you can see, the shock got relocated down to the lower arm as that was, as the semester went on, the Baja team kept telling us, please relocate this thing to the bottom. So is there one of their major concerns? Track width got increased to 62 inches. The regulations state a maximum track width of 64 inches measured from outside to outside tire. So we left 1 inch of room on each side for any adjustment that the team may have to make just later on. Camber at full compression now is negative 1.78 degrees compared to the negative 10 degrees I was seeing before. And then static caster got changed over to 9 degrees. That does not change throughout travel. It's plus or minus a quarter of a degree, mainly because the upper mount and the lower mount, the axes that the arm or the axes are parallel to each other and parallel to the center line of the vehicle, as well as the suspension travel got increased all the way up to 13.5 inches. So going into the analysis of our design, specifically the geometry. So the kingpin inclination angle, that was built into the knuckle. That was of 7 degrees. That is seen in picture 1 as if you're looking at the front of the vehicle and drew a line straight through the ball joints, that would be your steering axis. And then comparing that axis or the angle between that axis and the center of your tire, that is your kingpin angle. That was 7 degrees. That was found in literature to be a great value in Baja, so we just stuck with it. With caster, similar to kingpin angle, that is the same steering axis except looking from the side of the vehicle. That's 9 degrees throughout the entire travel, plus or minus quarter of a degree. And then camber, seen in picture 3 over there, with positive camber being the bottom of the tire being more inboard and negative camber being the bottom of the tire being more outward, had a static camber of negative 1.18. And then throughout the entire camber curve, it was relatively within negative 3.5 degrees all the way up to negative half a degree, which I'll go into in just a second. And then motion ratio, which ties into our suspension travel numbers, was found to be 1.68 inches, which in the previous or the current design on the vehicle is 1.3, which yielded a suspension travel of 13.5 inches. And then our control center and instantaneous center, one of the more overlooked things when designing a suspension, but our instant center, that is the axes that each tire of the vehicle rolls about. You get that center by drawing out 2 lines from the control arms out to a space that they intersect. And that is your instant center. And then to get roll center, you draw a line from your tire contact attach point or the center of your tire, and your instant centers and where they cross, that's your roll center, which is the center of which the entire vehicle rolls about. So the roll center was found to be 8.6 inches. That is 36% of our center of gravity height, as our center of gravity was 24 inches. Researching, it was found that between 20 to 40% of the center of gravity was recommended for off-road use. So we were just shy of that, 36%. And then going into our kinematic analysis, specifically with the camber, as that was one of the Baja team's main concerns. So we drew up a kinematic diagram, got the equations of for camber, and a plot was plotted on MATLAB, solving using those equations. As seen throughout the entire travel, it's pretty much -3 all the way to -0.5, with a going into slightly positive from ride height over here. That going into our tire patch contact. So using that graph, if you imagine a vertical line through the tire is greatly important through the travel of the vehicle, because you don't want the tire to push away. You kind of want it to roll through the travel, so it's more stable and doesn't see as many forces. So looking at that, you can see that through most of the travel, it stays pretty much vertical, just at pretty much full compression, full droop, it does stray away from that. So for load case analysis, 3 load cases were designed for our suspension. These were derived from dynamic loads seen in literature and other previous designs. So for our curb strike, a 4G lateral load was applied at a realistic curb height of 6 inches. And then with a 1G load at the center of the tire, those are all calculated, or the loads are calculated through the knuckle and tire to get the loads at the frame over ball joints. For the jump load, it was a 4G load at a 30-degree angle at the tire. So we decided on 30 degrees, as that is a realistic case of a vehicle landing on one tire and not flipping over yet. And then with the normal load of 1.5 times the normal force seen at that tire, so the weight of the vehicle at one tire, of half of that force being on the sidewall and half of it being on the bottom of the tire. So looking at the FEA boundary conditions specifically for jump load cases, as we haven't derived the curb and normal driving conditions, there were cylindrical supports at the chassis mount locations. And then for the lower, as well as the ball joint thread location, which were fixed in the Z and Y translation, as well as the rotation in the Y and Z. And then for the load case for the jump, for the lower, there was a remote force applied 993 pounds, 1 inch away from the thread of the ball joint, as that's where the center of the ball joint is. And for the lower, it was a reaction force of the shock applied at the shock mount of 275 foot-pounds in magnitude, which translates to an axial direction of 993 and a vertical direction of 2,750. For the FEA stress analysis, for the lower, it was found that the max stress was 20.5 kpsi, which yielded a factor of safety of 3.6, which was very surprising, especially with the bend nose incorporated in it. And then for the lower, the max stress was 82.1 kpsi, which is over our yield stress. However, it was in a weldment. If we do decide to ignore that, obviously some more analysis has to be done. Factor of safety is just over 1, as the next highest stress is 73.0, which is just under the yield stress. Some quality checks were done, like on average, the average stresses conversion under 5%, as well as reaction forces added up to hand calculations and the sum of moments as well.
We are still doing some analysis on what material selection we're going to use. The current car itself uses a 1020 steel tubing, and for the analysis, like Max said, for the FEA, we use 1020 just to have comparative values at the same material. The 1020 steel is very low cost. It's easy to manufacture. It has moderate strength and good ductility. And then we are going to be using we are probably going to be using the 4130 chromium steel, as that is the tubing that is used throughout the chassis of the cart. It is a high strength and lightweight material. It has an excellent fatigue strength and stiffness and resistance. But it does require careful welding and fabrication practices. Billet, we would like to use that for the lower if possible. It's definitely more costly than the other materials, but it offers significant weight to strength ratio. And it's commonly used for like components such as like knuckles, mounts, and brackets where stiffness is super important at high stress locations. The next material that we're considering is 1026, which is a higher carbon content than the 1020. So it is definitely stronger and it's more dimensionally accurate. It has a better weld consistency and joint fit up than the 1020, but it's a good balance of cost and strength. And then lastly, we have the alloy steel 4140 or 4340, which is a very high strength and fatigue resistance, but it's suitable for high stress and impacted loaded components, but it's definitely more difficult to machine and weld, and it's often needing like heat treatment after it is made. In summary, we've met most of our goals as the suspension travel was 13.5 inches and our goal was 8 inches. Our factor of safety is still unknown, as we did have a factor of safety that is above what we wanted for the upper, but as for the lower, we're still trying to figure that out. That kind of goes back into the material selection. And then we wanted an unsprung mass weight reduction of 15%. Currently, we're sitting at 6%, but that will hopefully go down once we choose different materials and have a finalized design. Our geometry, we were over our goals and the Baja team is happy with those values that we've produced. Our packaging has improved. It's still going to improve a little bit more once we have the gearbox and the steering set in stone. We did not have to redesign the chassis so much, which is a big help for the Baja team. And we are under our budget currently. And we also met all of the rule compliances, so that we would not be disqualified. For further investigations, like I said, we're going to be doing a material selection, which goes into the weight optimization. The shock mount is pretty much finalized, but it may need to be altered because again, the steering and gearbox are going to change that location. We are going to be continuing doing the FDA on the remaining load cases, which was the curb and then the normal riding. And then we're going to produce and test our system on the car itself to see how it performs compared to the previous design. And then these were the main sources that we used for our projects. And lastly, questions.
All right. I get to go first. Okay, nice. From the start, you gave some values for toe and camber and caster. Was that part of your project to decide what was good and what was bad, or was that just someone else on the team said this is what we want?
That was on us. Honestly, going into the semester, we did not have a project for a while. Steven has kind of told us, hey, the car's still not done. You guys are gonna do this, so then we just figure.
So specifically with the camber angle, I've seen a lot of various opinions on what's good for a Baja car and seen a lot of different designs. So I don't know where you got your. I see a lot of them that have the negative camber and then they want camber advance. Is it like want it to change in a particular way?
Yeah.
That it would go more negative as it deflects?
It really depends on the design of the Baja. Like,
yeah,
you have some where you have like twin I-beam. Those you can't really control camber curves. You're gonna.
But you can control your camber curve, and I guess my thought is, what do you can make it anything you want, right? And you kind of decided you wanted to keep it close to 0, more or less.
That comes from the introduction to AHA vehicle dynamics textbook
Okay,
that we got most of our geometry from there as well.
yeah,
as
I can't argue one way or the other. I'm just saying I've seen other approaches.
there are many approaches to it.
The motion ratio. That, so refresh my memory, is that basically the motion of the wheel relative to the compression of your shock?
That is from the chassis mount,
Yeah,
the length of the chassis mount to the center of the tire
Mhm.
over your shock mount location to the chassis mount.
okay, so if the shock is at an angle, that would be not exactly, okay. So 1.68, and it was previously,
Roughly 1.3.
so does that change the stress on your lower A-arm if you,
It does slightly. We had to play around with that.
Yeah.
Because we were trying to get a higher motion ratio to really improve the wheel travel, but we
but
were
that,
getting like 100 kPSI stresses and we
Yeah.
had to bring it.
so there's a big trade-off. So to get the motion you want, and you got more motion than you needed, but your stresses, one way to fix that is to put that motion ratio closer to the wheel.
Yeah.
And that'll reduce your bending stresses. So maybe don't settle exactly on that. If you're having problems with the stresses, rather than designing the A-arm, you can move that pickup point. And you saw 82 KSI specifically in a welded area.
Yeah,
Do you still have to resupply welding samples to the competition?
Yeah.
Are you able to measure the forces required to make it break?
so how the welding test goes is whoever's welding the vehicle.
Yeah, I'm familiar with the welding test.
So the material itself has to break before the weld goes.
Okay, so you have to do that. Can you do it in a way that you could also do an FEA of the welding test sample and measure the amount of force it took to break it and see, just to give yourself a little confidence, because when you get a result, an FEA result in a weld, it's really a big question mark. You don't know what those material properties are, and you don't really know what the geometry of that weld is. And so if you have a test and you're gonna do it anyway, I would suggest you should do a FEA of that as well and see if it agrees,
Yeah.
Because otherwise it's really a difficult thing to match FEA to reality. Good, that's all, those are my questions.
Following up, how to model the weld joint in it.
It was modeled in SolidWorks through the feature of the weld, and I was just imported into the FPA.
There was no specific.
No, there's no boundary condition.
And we just like refine the area there. For the proper mesh.
So the geometry of the model was whatever SolidWorks decided a weld looked like.
Yeah, I tried with SolidWorks to fix it to get a uniform like weld, but it just did not.
See, like there again, you could look at what you are actually getting
Yeah,
and measure it or evaluate it and then look at what the SolidWorks gave you.
In the material selection, I did not see any wall thickness choices included.
So our wall thickness on the vehicle right now is 0.65, and in our model, it is 0.63. So it's actually less than what was originally there.
however, in future selection, depending on which material we go with, whether it's the alloy, we can get away with a thinner wall. Versus going with like a 1020, which is currently used, we would more than likely have to go with what's on there, which wouldn't really have any weight.
And that's what I was getting to. The material selection in conjunction with the wall thickness will give you more choice. Yeah. I did not see any mention of fatigue failure. Did you primarily focus on static failure?
It was, so we used dynamic load factors, fatigue wasn't a key concern as the team was more focused on trying to keep the weight or reduce it, and these are relatively easy parts to manufacture, and they're building a vehicle every year, so it usually gets replaced.
What's the dynamic load factor?
What's that?
What's the dynamic load factor? How do you incorporate that?
Those are just factors to bring a dynamic load into a static load, so you don't have to do all the math.
Can you get like,
Like,
so you had some design loads? I'm just trying to understand, because it's a kind of a generic term and I don't really know how you would use it.
those mainly came from literature.
Mhm.
However, they are just ratio to pretty much bring a dynamic load. Like a jump, for example, the 4G load factor. People they get, I don't explain.
So let me ask, I'll just ask, so if the vehicle is on the ground.
Yeah.
There's a force on the wheel, you multiply that by 4 for a 4G impact, then you do multiply it again by the dynamic load factor?
No, so those load factors are the dynamic. Are,
The 4Gs?
yeah, the 4Gs is the load for that specific dynamic load.
So if you actually see 4Gs,
Yeah, if you actually see 4Gs, which that was a very conservative value, like last year's rear team used 2.3 Gs. And I mean, the military uses 4G to 6G.
And for the shock itself, that was predetermined, that was chosen for you?
Yeah, so currently, we are just gonna reuse the current shock that's on the vehicle with obviously more than likely adjusting the spring that's on there. They do have a sponsorship with Pure Shock, so, and they have provided a shock every year with them if they do require a change. But currently, we're trying to get away with the 8-inch stroke that the shock has.
And there's no damping, it's just a spring system.
It's a coilover, so you got the spring.
That's all I had.
any other questions? Well, you can ask three, all right, thank you.
I could find out more. That's weird. We're doing that really loud. Yeah. Yeah. Yeah, like we're in like one Baja, but then not really. It's weird.
Two separate sub teams.
Yeah.
Yeah, I got it, my schedule just didn't really reflect,
Yeah, the schedule just says one.
but it also on the time, it only shows,
The new one goes to 320.
Yeah.
I don't,
But
apparently.
yeah.
That's fine, that's all. I was confused for a moment, but I guess I got it. We all set? All right, whenever you're ready, take it away.
I'm Cody.
And then we're the second to the Baja. We're on the differential track assembly. So the background for it is the SA Baja in 2022 made a rule that the Baja vehicle had to have all-wheel drive. So they had to implement some new stuff to make the vehicle all-wheel drive. And then
in that the front differential is not optimized because it's like a new thing that they've had to introduce in the past couple of years. So it's not optimized for the competitive performance that they want. So that's why they asked us to redesign that, and then with that, the steering rack and assembly, to try and help cut weight. And then, so we had to look into all the rules regarding the steering, the front differential, and then anything else that would, play a role in that. So like I stated, the current issues are the excess weight of the parts, and then how much space they're occupying. And then, so our goals of the redesign are to decrease the overall weight, decrease the packaging, and we're doing that by integrating the two into one, not a true combined housing, but, combining them together. So this is a picture from the front of the vehicle looking down into the, pedal box. So the, rules regarding it, some rules regarding brake lines are that they can't be pinched or anything by any moving parts. That isn't too big of an issue for us because they've mounted the brakes and everything up and away from most of what we're dealing with. So it won't play too big of a role into our thing, but something we have to stay aware of. And then also there's a gearbox breather regulation rule. So if we use any fluid of any kind, we have to make sure that there's something similar to an ATV bellow so that there isn't any of that fluid leaking out onto the course or any surrounding area during the competition. Our design requirements, our objectives are to decrease the size and then get a 15% weight reduction. The steering geometry and axle alignments, we want it to be compatible with the current car so that it's easy to implement into the car. The steering rack needs to handle the feedback forces, so that, you know, can continue to function. And then we want to get the steering lock to roughly 90 degrees in either direction so that they have an easier time steering, during a competition and have better control over it. Some of our constraints are following all those rules, that Baja SAE has put out, and then, we don't want to mess with any of the framing or anything of the current vehicle because we want to have a design that can be implemented into the current vehicle. And then the input from the torque, our views and such from inside the differential, we need to be able to handle the input torque, and then the front differential ratio is set. Coming from the rear gearbox, it's a 2-to-1 ratio. And then the budget can't exceed over $1,000 unless we get additional funding.
So this is the current design. So right now it's this weird little box 2-piece design. Right now it has an incorrect ratio, so the front tires spin way too fast. 2 times as fast actually, because it needs a 2-to-1 ratio. Another issue with the current design is there's no seals, so you could run grease, you still kind of run the risk of the grease coming out of the gearbox, so the bearings do help with that, keeping all that in, but no seals is a big thing, because grease can get out, and then dust can get in, ruins bearings, ruins gears. Also, there's a lot of excess material, even though it is machined down, there's a lot that doesn't really circle around the gears. It's just kind of wide open and the gears are just kind of sitting there, so there's a lot of excess material that can be cut down. And then it's hard to manufacture, so talk to, Justin.
Yeah.
Talk to Justin, who does most of CNC around here, and talk to him about our design ideas and what direction we wanted to go, showed him a bunch of our ideas and what we thought would be the easiest to machine. And he remembered machining this and he said it was absolutely horrible. When you're machining those bearings, it's extremely hard that you have two different pieces. The A, get everything lined up perfectly, and B, get your tolerances, so bearings are nice and tight in there. So overall, this design was just a nightmare to machine. It could work if it had the correct gears in it, but there's a lot of things that could have been done better and they can be improved upon.
So these were my initial designs, coming up with it. The one on the left was the one that I first came up with. It's most similar to, what's currently on the card. Moving these rack basically down to the bottom half of what the box is. And then either integrating it, fully, having it be the same, fluid or grease or whatever in it. We thought about doing that. And then once we looked into that a little bit, we strayed away from that. So then figuring out a different way for it to be integrated into there. And then this was my second one that I just started mocking up. And came to the realization that if I got the, rack to the proper size, it'd take up way too much space. More towards the driver, which would cause a lot of issues for their feet and getting in and out of the vehicle quickly. And so we went away from that design.
These are my preliminary designs, so this one just kind of modeled the idea of combining both the gearbox and steering rack all in one. You could have it that it's split here. Another idea that you could have it split at the top here. So this is just like a rough shape that multiple things could be applied to. But I went towards more of a cylindrical shape as seen here. So this one has the rack fully integrated in it. It'd be machined into it. Another idea was we could cut the top off here, have it bolt on, and then it'd be a lot easier to machine the rest of the housing in the rack, not being a part of this. And then the final idea was making this that it comes off completely, that it bolts on to the differential housing, and that we have a removable cover, like a side cover that comes off, and that's how you get the gears. So just a more of an assembly rather than completely integrated as one CNC machine. So then we went into the decision matrix. So we weighted our cost, durability, weight, ease of manufacturing, compactness, ease of maintenance, and replaceability. Here we rated ease of manufacturing the highest because if you can't make the part, you can't use the part. And being that we don't have stuff like being able to cast stuff affordably here of this nature and more complex machining, that was a big thing that we wanted to make sure this thing can actually be used. Next was replaceability. Since it's an off-road vehicle, it takes a lot of stresses, a lot of forces. Things, it's not a matter of if things are gonna break, it's a matter of when things are gonna break. I've raced go-karts and cars for many years, and no matter what, things are going to break. And then we kind of weighted compactness, durability, and cost all the same. Just because we thought they were all important things that needed to be incorporated into it, and we couldn't really make sense of weighting one more than the other. And then the lowest two was ease of maintenance and weight. Sometimes when you're designing stuff, it's hard to get the weight, especially with the previous design. Due to the gear sizes being incorrect, it might end up being close in weight because we have to run a 2-to-1 ratio, and the gear is gonna be a lot bigger than the gear that's in there, diameter wise, which is gonna make it weigh a lot more. And them not having seals is another thing that adds weight. So it's hard to compare the two weight wise when one really needed to be improved upon. And then either maintenance, just making sure that if the bearings go out, the tools need to be changed. It's still relatively easy to do those things, so you don't have to take a ton of stuff apart. And then we took all of our design ideas, so we just kind of put like this weird 2-piece in one category here and then split up the cylindrical shape. And after we went through, we see that the cylindrical shape with the removable rack was the best overall. It didn't score the highest in every category, but it scored the most consistent overall. That's why we decided to go with that one. So the prototype that we came up with, so we plan on using 6061 T6 aluminum, and with that material, it weighs just under 7 pounds. It's pretty compact. It's 7.5 inches long, so from the very end here to the very end here, 7.5 inches. And then its width is 6.75. So that would be from this end cap to the identical end cap on the other side. It is 6.75 inches, 3/4. And then its height from the very bottom of the feet where it's gonna mount up to the top, it is 6.25 inches. So this design is meant to bolt into place exactly how they have the other one. As we saw in the earlier slides, that go back. So this guy right here, so it attaches with 4 bolts. So we're gonna keep that same design. That it's just like the ease of, they're not gonna have to modify the frame, that they can just bolt this piece right up to what they already have existing. And then these 2 tabs up here is where the steering rack is going to mount. Removable steering rack. For a few different reasons that we came up with is if you break the steering rack, you can just replace the rack itself. If you need to work on it on a bench, you don't have to take the whole differential housing out. So it's still one tight compact piece, and the only real loss is you just gain a little bit of weight with the bolts that are holding it on. And then came up with a separate side cover. So this is very similar to how ATVs and UTVs, most of them are set up. So this whole side piece will come off, and then you can slip in your main gear and then your pinion gear. And this was set up so from the bearings, it can be shimmed. They get the proper mesh between the gears. And there's another issue with the current setup is the mesh was completely horrible. There was maybe a 2 or 3 millimeter spot where you could see the gear mesh was actually lining up, which is horrible contact. And then another thing to for maintenance, it's really easiest to pop this cover off and pull the gears out if the gear gets damaged, or pop the cover off and then pound out the bearing, the seal, replace the bearing. Same with this. So all I gotta do is pull that cover off. You can pull the shaft out, change your pinion seal, your pinion bearings. And this design right now is set up that there's no supporting bearing on the inside. It's just gonna be a double roller or double ball bearing here that supports all that weight, and double just because as it's twisting in there, it's gonna have that much more contact that it's hitting, so it's less stress on those bearings. So this was a FEA analysis I ran on it. So we figured from the suspension team that roughly the bump steering was gonna be 250 pounds through the tie rod. And as you can see here, we had a very, very low equivalent stress of 677 PSI, and the piece did perfectly fine. Minimum factor safety is 15, which it's probably actually a lot more than 15. That's just what ANSYS capped out at for this. So it's plenty safe, plenty strong, just depending on the regular, normal, everyday driving conditions that the vehicle is going to experience. So it was fixed at the screw holes down here, and then the force was applied to the screw holes up here, just as the rack would be putting the force through that gearbox. And then this is the FEA analysis of the worst case scenario, which would be a crash. So the Baja vehicle currently goes about 20 miles an hour. and with a person in it weighing about 450 pounds. And when I did a very conservative, I thought, amount of stopping distance, which is 2 inches, hitting the very tip of the tire. And I say it's conservative because given that it's an off-road vehicle, you're running very low tire pressure, so the tire, as you hit the wall, is gonna give a lot, and as it comes back to suspension and everything will also have a little flex and give, so it's probably a lot greater distance than 2 inches, but that just gave a good idea of worst case scenario, what are we gonna see force wise if it's full on head on with one wheel into a wall. And you can see it's huge stress, if I'm used to stress, 2.93 times 10 to the second KSI. So a lot of force to be going through that. And the factor of safety at that point was about 0.14, which means the gearbox would fail. But our way around that is designing it so that we're using like grade A bolts. We're probably not gonna use something like that. We're gonna use bolts that if something like this would happen, it would shear the bolt off of the gearbox. You're not really concerned with trying to steer if you're already in a wall. And you just have to make sure that if it would shear off, the driver would be protected from the rack that it was applying it to them. But what's more likely is that the steering tie rods would never be able to hold a force like this. So once we get the setup exactly how we want it and dialed in more, we should be able to see at what point that the tie rods are gonna bend. That's the tie rods are another big point. But this is just absolutely worst case scenario. If the tie rod, it's just like a perfect straight force, if there's no bending in it, delivers all that force straight into the rack, then that rack delivers it straight into the gearbox. And then a few things that need to be determined is the exact gears that will be used. So I really wanted to use gears that were in an ATV. They've already went through all the work of designing them, making sure they're strong, if they have a good contact pattern. And there's something that you'd be easily be able to set up in the housing and get a good contact pattern is. The issue is most ATV gears are like a 3.5 to 1 or 3.7 around that range. So there's really no chance of us finding one. I've looked for hours, I've looked at all different brands, different makes. I've spent a lot of time trying to find one that would work just because it'd be a lot nicer for the design. It'd be quieter, smoother. So there's a reason why bevel gears aren't used in gearboxes, but worst case, we could use bevel gears. They have a lower contact pattern, usually 1 tooth at a time. The pattern isn't as great, they're noisy. They're pretty good for high torque applications, but something like a car where it's kind of decently high torque, but you're also using it constantly at that high torque. It's just not the best design. But it would work, and that's what they are currently using. I need to figure out exactly what bearings would be used, seals, and then I'd like to optimize the weight a little bit more of the housing once to make sure. I'm still kind of looking at gears. The best ratio I found was a 2.13 to 1 out of a Chinese UTV, and you can buy a variable differential housing. Only issue is it's a little bit off, but you can kind of counteract the gear ratio being off by changing tire diameter. So worst case, you could throw a little bit bigger tire on the front that kind of help balance that out. And then the other scenario is if they're only using, because Baja updated their rules that you can turn your 4-wheel drive on and off depending on the event. You don't have to have it on full time because I have issues with people not being complete, not having 4-wheel drive. So stuff like the rock climbing and mud bog event, if it is more like a 2.13 to 1 ratio, it might not matter that much because it's kind of a lower grip scenario that the tires would just spin rather than creating the issue of the gearboxes binding up, but that's still not ideal. And then the steering rack, we still gotta modify the tooth count to get to the desired 90 degrees, and then we're either gonna modify the current case or create an adapter to run the current case on the gear setup. And then screw size and strength needs to be determined so that if we do go with shearing, that it hits and shears off properly.
Um. Just going back to the beginning, you said that even in the gearbox that they have now, it has an incorrect ratio of 1:1.
Yep.
And it's supposed to be what?
2-to-1.
And why?
Why?
Yeah.
That's, I don't know, someone did the math wrong or something in the rear.
I mean, why should it be 2:1?
Because the rear tires spin once and the front tires spin twice with the 1-to-1 ratio in the front.
Because they're different size.
Pinion gear, so that 2-to-1, so front tires and rear tires are both spinning 1-to-1 ratio. Because right now the front tires are spinning twice as fast as the rear.
So you drive that car? Are the tires the same diameter?
Yes.
Yeah.
And you drive it in a straight line and the fronts are trying to spin twice as fast?
Yeah, so that's what the
So the drive shaft coming up from the rear spins twice for every rear rotation.
Yeah.
So we don't know who messed that up, but that's how it's currently set up.
Okay, well, that's an easy problem to fix. I mean, if that's what you need, right?
Yeah.
So then on your design concepts that you showed, you had like some drawings that basically look like a box with some shafts coming out. What was different? Like, I wasn't really sure what was different, just different layout and what was in there. I'm not sure what you were like those.
So currently.
Oh, go to your concepts.
Yeah.
Mhm.
So that's from the one angle, this is from the other angle. The steering rack is on that piece that's mounted at an angle.
Sure.
Completely separate from the differential right there.
Mhm.
So this design was just implemented instead of it being a separate piece mounted up top here, having it.
What is that you just pointed to? This,
Just the empty space back here. I'm talking about that triangle.
that's the steering rack.
That's the steering rack, this is the gearbox.
So there's how many different shafts on there?
This is the axle. Right wheel, left wheel, and then this is the tie rod coming out to each wheel. This is up to the steering column, and then this is the drive shaft.
Okay, so when you show these concepts, none of what you just said is apparent at all. It just looks like a gray box with a bunch of.
Yeah.
So I had no, I had no clue what you were trying to present here and what this even represents. And you needed to do a lot better job of explaining. And so the one on the left and the one on the right, what's better or worse about these two?
So this one is to implement into the current car.
Why?
Setup, because the steering rack is in the back, more similar to how it's set up currently, which keeps the steering column further away from the driver's seat.
Towards the back, meaning?
Towards the front of the car, sorry.
Okay.
From this view, but towards the front of the car.
And-
And so the steering column is
Okay.
out of the.
So more towards the front of the car, away from the driver. That makes sense.
And this one has it, so it's more in between, closer to their knees.
Uh-huh. And what's the advantage of this one then?
This was to try and make it so that there wasn't as much space in front. It's also, it's better steering to have it behind the axles because of
Okay.
accident steering. So it's the attempt to get it back there, but due to the height, restriction that we have, try not to take up too much space from,
Okay. Thank you. That all makes a lot more sense now that you explained it, but then like, just so you know, the first time through,
yeah, sure.
I had no, like, it would help to know what's the front of the vehicle, back of the vehicle, where the drivers are, pluses and minuses of those designs. Thank you. In your constraints and criteria table, you had weight, the weight of the system as 5%. And that in the beginning of your presentation, that was the first thing you mentioned as one of your goals. And
Oh.
that seems a little odd that,
So we want to have it down. The compactness is kind of what we need way more in this, because if we get it compact, it'll decrease the weight. But the weight of each individual part might not be as, great of a reduction. Because like the differential housing is gonna have a weight reduction, but might not be as great as the overall weight reduction because.
so the way to do that is like your weight criteria should be of the whole system. You don't really care what individual components weigh if the weight of the vehicle goes down, right?
Yeah, so we just did it wrong on that sense, because like, on that matrix, we're not accounting for like taking this piece off and
So,
reducing that.
In your report, did you explain what you meant by weight?
I believe so, yeah.
Like you don't optimize the weight of a vehicle
Yeah.
by optimizing one component at a time. You gotta kind of look at the whole design and say which design is gonna give me the lightest system.
Yeah, overall.
And that was the whole point of the differential. Is to make it more
Sure.
and to save weight from all the brackets.
That completely makes sense, but just the way it was presented with your decision matrix, the way it was presented didn't make sense. Okay. In your FEA analysis, what did you, so in the one case, you said the ANSYS capped out at a safety factor of 15.
Yeah, so that's just.
What do you mean by ANSYS capped out?
It doesn't tell you a safety factor over 15. The highest value it displays is 15 for safety factor. So it's just in there saying.
So did that mean
minimum safety factor was over?
how would you get past that?
You could go in and.
Like, is it 16 or is it 50?
You could go in and look at the. Normal calculate safety factor.
Or you could change your loading?
Yeah.
But
I didn't think it's necessary. It's just.
Why don't you just do stress analysis instead of having it do safety factor?
I did. So stress analysis.
Oh, okay. So you could figure out a safety factor.
Yeah.
Yeah, that would be better than just saying it's something more than 15.
It's more like just saying under normal driving conditions, it's gonna be more than fine, that the minimum safety factor is well over 15.
I think it would be better to put a real number on it rather than saying, I don't know what it is, but it's more than 15. I'll let you go. No questions. All right, good. Any other questions? Thank you. Yeah, we're done.
Gather the.
I got here at 1:30.
Better call me, because you're here at like
There we go.
24 or something. You're going to go.